In this video, we're going to talk about H NMR spectroscopy. We're going to go over a few basic things like chemical shifts, spin splitting, and how to identify the right compound in a multiple choice question. And also to determine how many signals you would get in the H NMR spectra if you're given a molecule. So those are the most common questions that you'll see on an exam. So we're going to focus on that. So let's go over some important chemical shifts that you just have to know for your exam. If you have a carboxylic acid, you need to know that the chemical shift is going to be anywhere between 10 to 12 ppms. For an aldehyde, the hydrogen red is going to be about 9 to 10. And for a benzene ring, if the hydrogen is directly attached to the benzene ring, it's usually about 6.5 to 8.5. If the hydrogen is on a carbon one away from the benzene ring, like on a benzylic carbon, it's somewhere between 2 and 2.5. Now, if you have a hydrogen directly attached to an alkene, usually it's about 4.5 to 6.5. And if you have like a CH2 directly attached to a halogen, like a bromine, chlorine, or another electronegative atom like nitrogen or oxygen, these hydrogens on the CH2, it can vary between like 2.5 to 4.5, but typically it's usually between 3 and 4. So let's say 2.5 on the low side, 4.5 on the high side, but most of the time 3 to 4. And this methyl ketone, or a CH3 next to a carbonyl group, that is going to be around 2 to 2.5 as well. Usually around 2.3, but somewhere in that range. Now here we have a tertiary carbon, secondary, and a primary. The primary carbons are usually upfield. Upfield, the numbers are lower, like 1 and 2. Downfield, it's higher, like 10, 11, 12. So upfield signals are towards the right. Downfield signals are towards the left. So the primary carbons, those hydrogens attached to the primary carbons, are usually upfield. It could be a little bit less than 1, maybe like 0.8, 0.9. A secondary CH2 group is a little bit more than 1, maybe like 1.1, 1.2. And the tertiary CH could be a little bit higher, like 1.4, 1.5. But if you have a regular CH3 that is attached to like another CH2 and there's nothing special around it, it's usually around 1 to 1.5. Just a ballpark estimate. Alright, so let's go over some examples. So let's analyze this particular compound. Let's say if we have 2-bromobutane. So we're going to write it as a condensed structure. CH3, CH2, CH, CH3. So what do you think the chemical shifts are for these hydrogen atoms? There's 4 different signals. Each of the 3 hydrogen atoms on this carbon is part of the same signal because those 3 hydrogens have the same exact electronic environment. So they show up as one signal. Let's call this protons A, B, C, and D. There's 4 different types of hydrogens in this compound, so we're going to get 4 signals. Now let's write the chemical shifts. So the proton A, that's just a regular CH3, it's primary, so we can say it might be like 0.9. For D, it's also primary, but it's closer to the carbon with the bromine, and that carbon has a partial positive charge. So the CH3 on the right should be a little bit more downfield than the CH3 on the left. So let's say like 1.0. Now, the CH2, which is secondary, that could be a little bit more than 1, maybe like 1.1. And the CH, which is directly attached to a bromine, that's going to be anywhere between 3 to 4, so we'll say like 3.5. So those are the chemical shifts. So on the graph, let's say if this is 0, this is 1, this is 2, and this is 3, and 4. So proton A would be somewhere around 1, but we'll graph it soon, actually. Let's look at the spin splitting pattern. So looking at protons A, the CH3 is adjacent to a CH2, and you have to use the N+ rule for the number of hydrogens on the adjacent carbon. So this CH3 is adjacent to a CH2 group, so you have to look at those two hydrogens, add one to it, and you're going to get 3. So 3 is a triplet, and a triplet is going to look like this. So that's a triplet. As you can see, that one signal is split into 3. Now let's look at the CH2 proton, the protons that correspond to signal B. On the left we have a CH3, and on the right we have a CH. So it's adjacent to a total of 4 hydrogens. Using the n+1 rule, we need to add one to it, so it's going to be 5, which is like a quintet. So around 1.1, we're going to have something that looks like this. Now at 3.5, we have a CH that is adjacent to a CH2 and a CH3. So it's adjacent to 5 hydrogens. If you add one, you get 6. So that's like a multiplet. And the splitting pattern for 6 is you have 2 in the middle, then another 2 on the right, and then another 2. As you move away from the center, you have to go in a downward direction, but you want to split it evenly. So around 3.5, we should have a signal that looks like that. And around 1.1, we have this signal. Now we have another signal at 1.0. And that CH3 is adjacent to a CH, so it's adjacent to 1 hydrogen. If you add one to it, it's going to be a doublet. And so it's going to look like this. So let's see if I can put that on the left side. Now, sometimes you might see something called integration. And notice that there's 3 hydrogens on the methyl group. So sometimes you might see 3H above that signal. So for this triplet, we might have a 3H. Now here we have a CH2 at 1.1. So this you might see as a 2H. And a doublet corresponds to a CH3, so you might see 3H above the doublet. And for the signal at 3.5, the CH, you'll see like 1H. So if you see these numbers on a test, this corresponds to a CH, that's a CH2, CH3, CH3. It can help you to distinguish one answer from another. But really, the integration peaks represents the area under the curve. But on a typical exam, you don't have to worry about that. If you see 3 hydrogens, it usually corresponds to a CH3. If you were to see like 6 hydrogens, it would correspond to 2 CH3s attached to the same carbon. Since these are identical, they add up, and they add up to 6 hydrogens. So this represents really like the number of equivalent hydrogens, so to speak. Okay, let's look at another example. Let's say if we have this compound. Let's identify the different types of signals that we see. Now the 3 methyl groups on the quaternary carbon, they're identical, so they correspond to the same signal. So we're going to call it signal A. They have the same exact chemical or electronic environment. The CH2 it's going to be signal B. It's unique. The CH2 that's next to a carbonyl group, that's different from the other CH2 on the left, so we're going to call it signal C, and this is signal D. So we have 4 different signals in this structure. Now, these CH3s, if you look at the adjacent carbon, which is this, there's no hydrogen, so it's going to be 0 plus 1, so it's going to be a singlet. Looking at the splitting pattern for the CH2, there are no adjacent hydrogens, so 0 plus 1, that's a singlet as well. This CH2 is adjacent to a CH3, so 3 plus 1, that's 4, it's going to be a quartet. And this CH3 is adjacent to a CH2, 2 plus 1 is 3, it's going to be a triplet. Now, let's look at the chemical shifts. This CH3 is primary, so we should say the signal is going to be around 1. Here, the CH2 is attached to an oxygen, an electronegative atom. So it could be anywhere from 3 to 4, that's going to be like 3.5. And here, the CH2 is, signal C is directly attached to a carbonyl group, so that could be like 2.3. And here we have a CH3 that's just attached to a CH2, and it's primary, so it could be like close to 1, let's say like 0.9. So once you have the signals and the splitting pattern, that's usually good enough to ID like the right answer. But let's also mention the integration. So signal A has 9 equivalent hydrogens, so it should appear as 9H. This will appear as 2H, 2H, and 3H. So those are some things that you want to know. Now, one type of question that you might see on an exam, a very common question, is they'll give you a structure, and you need to be able to identify quickly how many signals will appear in the graph of the H NMR spectrum. So what you really have to do is identify which hydrogens are equivalent and which are not. These methyl groups are equivalent because they're attached to the same secondary carbon, and they're both primary. So if you can identify the different types of carbons, you can quickly see which are equivalent. So both of these primary carbons are the same. They're attached to the same secondary carbon, but the primary carbon on the right is different because it's attached to a different secondary carbon. Oh, I made a mistake. This is supposed to be tertiary, actually. So those two primary carbons are attached to a tertiary carbon. Now this is going to be signal C, this is signal D. Everything else is different. So there are 4 signals that will be found in that compound. So now what about hexane? How many different signals do we have in this compound? So this is primary, and the ones in the middle are secondary. Notice that these 2 primary carbons are identical, so the CH3s attached to them are equivalent, so they would show up as signal A. Now these 2 are equivalent. They will show up as signal B. They have the same exact environment. If we analyze this secondary carbon, it's adjacent to a primary and a secondary. And this secondary carbon is also adjacent to a secondary and a primary. So they're the same. If you notice, if you split this molecule in the middle, you can see it's symmetrical across that line. So these 2 are equidistant from the line of symmetry, so they're the same. And these 2 are equidistant from it. And the 2 secondary carbons that are equidistant from that line is these 2, so they would appear as signal C. So there should be 3 signals on this compound in the H NMR spectrum. So now, what about this compound? How many different signals are there? Now notice that there's no symmetry in this molecule. Everything is different. This is going to be signal A, B, C, and D. Now remember, we're focusing on H NMR, not C NMR. So for H NMR, you focus on the hydrogens. We didn't count this one because there's no hydrogens attached to it. If we were dealing with C NMR, we would have 5 signals instead of 4. But since we're dealing with H NMR, there's only 4 different types of hydrogens. So let's consider this particular compound, paraxylene. It has 2 methyl groups para with respect to each other. So how many different signals would you expect in the H NMR spectrum of this graph? So notice that we have a line of symmetry. So across the horizontal line, these signals are identical to each other. And these signals are identical to each other as well. Now, there's no hydrogen atoms on this carbon. So we shouldn't see a signal there in H NMR. But for C NMR, you would. Now, notice that we can also draw a vertical line of symmetry. So across the vertical line, these 2 are identical to each other. So all 4 of those CH bonds are similar. So therefore, there's only 2 signals in this particular molecule. Now, being able to identify the number of signals in a compound will help you to distinguish a wrong answer from a right answer. And if you have a multiple choice test, the process of elimination will help you to ID the right answer. So let's try a few more examples. So let's say if we have this particular compound, methoxybenzene. Actually, this is ethoxybenzene. How many signals would you expect in the H NMR spectrum of this graph? Or this compound? Feel free to pause the video and see if you can get the answer yourself. So this CH3 is unique. That's going to be signal A. Here we have signal B. There's no hydrogens on this carbon atom. Now, the line of symmetry will be here in the ring. So therefore, this will be signal C, D, and this one is unique, so it's going to be E. So we therefore have 5 signals in this particular molecule. So for our last example, try this one. And then we'll work on a few multiple choice problems. So how many signals would you expect to be in this molecule in the H NMR spectrum? So where is the line of symmetry? It might be hard to see here, but let's say if we draw it this way. Notice that A and B will be identical to each other. However, we can also draw it this way. So these two are identical to each other as well. So all those 3 methyl groups are identical to each other. So each of these methyl groups are the same, so they would show up as one signal. We'll call it signal A. Now there's a hydrogen on those carbons, and they have the same exact chemical environment. Each hydrogen is between 2 methyl groups, and they're equally distant, so those hydrogens are identical as well. And there's no hydrogens on the tertiary carbons, so due to the double bond. Therefore, there's only 2 signals in this particular molecule. So let's try this particular multiple choice problem. So which of the following compounds is most consistent with this spectrum? So first, let's identify the number of signals. In compound A, we can see that there's 3 signals. There's 3 different hydrogens. Compound C, we can eliminate. We have a benzene ring, and usually the signal for that, for the hydrogen on the benzene ring, is about 6.5 to 8.5. And we don't have no signals in this region, so we can eliminate answer choice C. Now, if we look at compound B, notice that the methyl groups are identical to each other. And so compound B only has 2 different signals, but here we need 3 different signals. So we can eliminate compound B. So we're between D and A. If you notice, both D and A have 3 different signals. This is signal A, B, and C, and so forth. So now we need to look at another difference. Let's look at the chemical shifts. For compound A, a regular CH3 would be somewhere around 1. And this CH2, which is secondary, may be a little bit more than 1. Let's say like 1.2. And the CH2 that's attached to a chlorine would usually be between 3 to 4. Now, we don't have anything in 3 to 4, so that means we can eliminate A. If you look at answer choice D, this methyl would have a signal of around 1. The CH2 that's next to the carbonyl group could be maybe like 2.2. It could be anywhere between 2 to 2.5. And the same is true for this methyl attached to the carbonyl group. It should be anywhere from 2 to 2.5, so this could be like 2.3 or 2.4. Now, D is most consistent with the structure that we have. We have a signal at 1, and there are 2 signals between 2 and 2.5. So answer choice D is the correct answer. Now, to confirm the answer, you can look at the splitting pattern. Here, this methyl group is adjacent to the carbon that it's adjacent to has no hydrogen, so therefore, using the n+1 rule, is 0 plus 1, it's going to appear as a singlet. And we do have a singlet around 2.4. Now this CH2 is adjacent to a CH3, so 3 plus 1 is 4. It should appear as a quartet. We do have a quartet here. And looking at the CH3 on this side, that CH3 is adjacent to a CH2, so 2 plus 1 is 3. We should have a triplet, and we do indeed have a triplet at 1. So answer choice D really matches the graph that we have. Number 2, which of the following compounds is most consistent with this spectrum? So take a minute, feel free to pause the video and see if you can get the right answer. So do you think the answer is A, B, C, or D? Now notice that we have a few different functional groups. We have an aldehyde, carboxylic acid, a benzene ring, and a ketone. If you see an aldehyde, look for a signal between 9 and 10. Since there's no signal in this region, we know we can eliminate answer choice A. It's not going to be an aldehyde. We shouldn't have an aldehyde in the answer. So the next thing that we can eliminate is the carboxylic acid. We should get a signal between 10 and 12, which should be somewhere in this region. And since we don't have that, B cannot be the right answer. So now the next thing we could look at is the number of signals. So we have 4 different signals. 1, 2, 3, 4. Let's look at D. For answer choice D, we can see that there's a line of symmetry, a vertical line of symmetry that we can draw between the two methyl groups. So the methyl groups would have the same signal A. This is going to be signal B. These two are identical. That's C, D, and E. So notice that answer choice D has 5 signals, not 4. So it's eliminated. Now if we look at answer choice C, we have 4 signals. The methyl group on the left, that's part of an ether. The methyl group that's on the right, that's part next to the ketone. And then the hydrogens that are attached to the benzene ring. So if we draw a line of symmetry across the benzene ring, we can say this is proton C, they're identical, and here we have proton D. So we have 4 signals. So C is the correct answer. But let's analyze it a little bit more. So the methyl group next to the carbonyl group, that should be around 2 to 2.5. And so let's say 2.3. And notice that it's adjacent to no other, it doesn't have an adjacent carbon with hydrogen atoms. This carbon has no hydrogen atoms, so therefore the splitting pattern is 0 plus 1. It should appear as a singlet. And that's what we have here. This signal is a singlet. And it's around 2.3. Now, a methyl group directly attached to an oxygen should have a signal between 3 to 4. And since there are no adjacent hydrogens next to it, it's going to be a singlet. And that's what we have here. So this corresponds to the methoxy group. And so clearly we can see answer choice C is the right answer. Number 3, which of the following compounds is most consistent with the spectrum? So do you think it's A, B, C, or D? Take a minute, feel free to try it out and see if you can get the answer yourself. So the first thing I'm going to look at is the number of signals. Looking at answer choice A, we have 1, 2, 3 different hydrogens. So we have a total of 3 signals. And the graph has 3 signals, so A is okay. B also has 3 different hydrogens. None of them are equivalent. So, C has 3 signals, not B. Well, B has 3 signals as well. All of the hydrogens are different. So now what about D? How many signals do you see for answer choice D? Notice that these 2 methyl groups are identical because they're attached to the same CH group. So therefore we can call it signal A. This is going to be signal B, it's different, and signal C. So even D has 3 signals. So the number of signals didn't help us in this problem. So we need to look at another difference. Let's look at the integration peaks. So here we have a 2H, which corresponds to a CH2, and a 3H and a 3H, which corresponds to 2 separate CH3s. Here, this will be a 3H, 2H, 3H, so A is okay. Looking at B, we have a 3H, 2H, 3H, so B is okay. Answer choice C also has a 3H, 2H, and a 3H. But looking at D, these 2 methyl groups, they're equivalent, and so therefore we have 6 equivalent hydrogens. So if D were correct, we should have a 6H signal. Since we don't have it, D is out. And also, if you look at this signal, that's supposed to be a 1H and a 3H. So D doesn't correspond to the graph that we have, so D is eliminated. So now what else can we do to distinguish between A, B, and C? So now let's move on to chemical shifts. Let's analyze answer choice A. The methyl group on the right would have a signal around 1. Now the CH2 is directly attached to the oxygen, so it should be around 3 to 4, so let's say 3.5. And the methyl on the left that's next to the carbonyl group, that should be around maybe between 2 and 2.5, so let's say 2.3. Now this signal is around 3.5, and we do have a signal of around like 2.3 and a signal at 1. So we can't eliminate answer choice A right now. So let's move on to B. This methyl group is going to be around 1. The CH2 next to the carbonyl group is about 2.3. And this CH3, which is attached to an O, that could be around 3.5. So A and B have the same chemical shift. Slightly different, but B can still correspond to that spectrum, so we can't eliminate A or B. Now let's move on to C. This methyl group should have a signal of around 2.3. It's next to the carbonyl group. Now this CH3 is directly attached to an O, so that should be like 3.5. And then notice that we have a CH2 directly attached to an O and next to a carbonyl group. So the combined effects of those two it should push it more to the left than 3.5. It could be maybe 4 or even higher, maybe like 4.5. Either case, we don't have a signal at 1. So therefore, C is eliminated. So now, to distinguish between A and B, we need to look at the spin-spin split-in pattern. So let's look at A. Starting with the methyl group on the right, it's adjacent to a CH2. So using the n+1 rule, 2 plus 1 is 3. So 3 would correspond to a triplet. So at 1, we do have a triplet, so that is good. Looking at the CH2, it's adjacent to a CH3. So 3 plus 1 is 4. 4 represents a quartet. We do have a quartet between 3 to 4, so that's good. And looking at the CH3 on the left, it's not adjacent to any carbons that has hydrogen, so 0 plus 1, it's a singlet. And we do have a singlet at 2.3. So right now, A looks good. A completely matches the graph, so A is the correct answer, but let's see why B is not the right answer. So looking at this methyl group on the right side, we can see that it's adjacent to a CH2, so it should be a triplet. At 1, we do have the triplet, so that's good. Now this CH2, which is at 2.3, should be a quartet. It's adjacent to a CH3, 3 plus 1 is 4. And we don't have a quartet at 2.3. We have a singlet. And if you look at the CH3, that should be a singlet at 3.5, but we have a quartet at 3.5. So B, the splitting pattern doesn't match up. So the correct answer for this particular problem is answer choice A. And if you have a standardized multiple choice exam, that's what you want to do. You want to look for differences. You want to eliminate the wrong answer until you get the right answer. So what I would do is first look at any functional groups. See if you have any aldehydes, any benzene rings, carboxylic acids, and start from there. Then move on to like maybe integration peaks or chemical shifts. And then for last, use the splitting pattern for last, because that takes more time, and sometimes you could eliminate all the wrong answers and get the right one without even using that. But save that as the last resort. And also, don't forget to count the number of signals, because that's another way in which you could distinguish the right answer from the wrong one.